notes, chicken scratch, and scratch paper all work the same.
All right, so we're going to start talking about logs. Logs are simply a way to condense large values of data down into more manageable levels. It's also able to provide more information. So if we were to look at this graph, zoom in maybe, come on. There we go. Okay, so this is what a log graph looks like. So we still are covering the same thing. We have our major divisions just like we would a regular graph. But as we get farther to one side, those divisions start becoming closer and closer together. You will see this scale on analog meters and things like that. You'll see they'll start out pretty big and then things will start getting more and more down because it takes more and more energy to move smaller amounts. It's kind of like the exponential curve. As things get larger and larger, things are just going to take off. If we were to look at this data in just like a regular graph, what it would look like is this. So it takes a curve and it flattens it out so it's easier to look at it. It also can, the problem is sometimes if we get into like this area down in here, it'll actually hide information. It hides variances and it hides things like that, which we may or may not want. There's times where, yes, we want to hide some anomalies and the logarithm kind of takes care of that and smooths it out for us. Because if we were to zoom into this section, what we might see is the line would come up and then it has a little bit of a spike and then continues. Sometimes those are just anomalous readings. Sometimes they actually mean something. But in the grand scale of things, we want to be able to look at things linearly. The human mind works linearly. You have to go from point A to point B. When you start looking into curves, graphing curves like that, that's when things start, getting nuts and getting crazy. The other idea behind this is we're going to talk about Moore's Law in a minute too with some of these. And we're going to have you guys work out some of those. Moore's Law simply states that the physical size every year and a half of memory gets cut in half, where the actual storage value of it, the amount of bytes that it has, doubles. So we're cutting it down physically in half every year and a half, but we're doubling the amount of memory that it can hold. Because if you guys look today, what can you buy really quick off of just for flash drives? Terabytes are not uncommon. See if I can get this to work. I'm going to use your website. Flash drive. First thing that comes up, 32 gig hard drive. That's what it is. Even though it's a flash drive, it's a 32 gig hard drive. Okay? I'm gonna date myself a little bit. When I was first going to college, this was unheard of. You couldn't get 32 gigabyte hard drives just off the shelf. We still had a few 256 meg floating around. Yeah. Okay. The common one was 512s and starting into the 1 gig. 4 gig was starting to get commonplace when I graduated the program the first time when I got my associate's degree in 2010. That was standard, was 4 gig. With my associate's degree. So I graduated with my associate's degree in 2010. I graduated with my bachelor's in 2015. Yeah. Right. And so what we're going to do is we can actually go through and we'll calculate. We'll probably talk about this tomorrow because I got to find my paper. But we'll find out how long it's going to take us to reach certain values of memory. Like, it's insane how quick this is coming. It's getting smaller.
Well, like respectively they are, but there's more draws. So like Minesweeper takes up like 10 megabytes on my computer. Small. Yeah.
but then Call of Duty is out here with like 220 gigabytes when Medal of Honor was 8 gigabytes.
Yeah. Like I said, we're using that memory as fast as we can create it and we can have it in place. We can use it. Okay. Another example. At Costco right now, you can get a 5 terabyte hard drive for $105 off the shelf. You can walk up and grab it. When I started my bachelor's program in 2010, the same year I got married, well, the year after, my wife, for an anniversary present, got me one of these Seagate backup portable hard drives. It was 2 terabytes. It was $140. In 2010, we've gone up 3 times the amount of size. And that was the thing too, is they had this style, these backup drives that were, this one's an 8 terabyte, but you have to plug this one in separately to its own power source. These guys, you just plug in with the friggin' USB port. Okay? And that's what I wanted. So my wife told me I can get another one when I fill up my 2 terabyte. I'm about 3/4 of the way there. I'm taking all my DVDs and my movies that I have at home, and I'm converting them to digital formats, which is legal because I have a backup copy of my original disc. If you don't own the disc, you can't do it. That's the difference. And so I'm trying to put all my DVDs in one place because this is so much easier to watch videos with. We don't have to find the stupid DVD. We don't have to make sure it's not scratched to hell. The kids can even plug this in, and it's not going to mess it up too bad unless they, drop it, hit it, drool on it, that kind of stuff. When you're little, these things are toys for little kids, and they love to chew on them. So, but like I said, nowadays, so for cheaper than what I got my 2 terabyte one, I can get a larger one. Micro SD cards. Okay? Yeah. Some phones will support those. A lot of the phones won't support anything over 128 right now. Yeah.
It doesn't make sense to me though. It's so small. What the heck?
Yeah, that's what I'm saying, is these things are getting smaller and smaller and smaller. But they're getting doubling up. That's how, and this is how logarithms work. We're going to be able to take these logarithms and use them in such a way that we can start predicting things in the future. Because like I said, every year and a half, we double the size and half the amount of physical space it takes up. So one of the things we'll look into, and I'll pull this out, is like I said, we're going to calculate how long it's going to take to get to a certain value, and how much the relative cost it's going to be. And even the sad thing is, I put this together a year ago. The data is already obsolete. What the amount of the values that I calculated are already obsolete in a year. I think it's picking up speed.
That's kind of cool. One day we're going to download our brains.
Yeah. So, well, and here's the thing too, is like the amount of, if you think about the amount of information that you put in your head and the amount of information you retain. So one of these videos that I make for class, they're less than an hour long. They are just over 4 gigs of data. And I'm not recording much. I'm recording this screen, I'm recording my voice. There's not even lots of picture changes going on. I'm scrolling and things like that, but I'm not showing animations, I'm not showing movies. A normal DVD is about 4.5 gigs. So an hour and a half movie, 2-hour movie is 4.5 gigs of data. How much information of that do you remember? How many stupid movies can you just pull up in your head and start playing? Like, the amount of memory that our brains hold is amazing. And if we could ever get to the point where we have the capacity to download somebody's brain, that's crazy. Like, just the amount of space that we'd have to have. I mean, we're talking well into, let's see, gig tera. We're probably talking 10 to the 28th power of bytes of memory. Because think about it, every word that you know, every phrase, you do that. If you don't know English, you know a good chunk of material. But what if you know that exact same material and can translate it into Spanish? That same material, you can translate it into French, okay? By knowing 3 different languages, now all of a sudden you've tripled the amount of memory that you have personally. Well, I mean, everybody has access to that, but that's what I'm saying is the amount of knowledge that is contained in your head, it's insane how much there is. When we think of all these robots that we try to program, even with Atlas, even programmed in there, that's still billions and billions of lines of code to get them to function and to make decisions, and I use that term very loosely, pre-programmed instructions. Once we're able to finally capture the essence of what makes us us and the brain power behind it, that is going to unlock so many technologies. We probably will have a robot workforce that completely annihilates ourselves if we get to that point. In all honesty, that's probably what's going to happen. When we finally unlock how much storage the brain has and is able to use that, we're in trouble. Let's be honest, we're in trouble.
Terminator.
Yeah, worse than the Terminator.
You think that we're technically pre-programmed because we're told like how to react to situations and we take the information on how to react and that's how we
To some extent, yes. And that's part of growing up. Is you get pre-programmed to certain instructions, but your brain still has the ability to make decisions that were not pre-programmed into you. That's why when your parents go, "The hell did this come from?" They're like, "We taught you this is right, this is wrong, but yet you created a third path." Like that happens all the time. Yeah, it comes into instinct. It comes into, how you're feeling at the time. That's one thing that we haven't been able to duplicate yet, and honestly, I think, thank goodness, is duplicate feelings in robots.
Well, like the CPR video we watched, where they're kicking it and like knocking it over.
And it finally just snapped.
And it's like, okay,
I feel like the dog would have been able to run next to it.
Yeah. That's like I said, with decisions and with the electronic side of things, that's the hard part that we have to try and incorporate. And that's what we're trying to do, is we're trying to mimic the knowledge and everything that we have. And that's one of the reasons we're in this, is we're trying to get to that point to push this technology farther. Even if you're not the lead engineer on a project, even if you're the one building and maintaining the robots or the computers that are doing it, it's still amazing. Nobody that I've talked to that worked at NASA has regretted doing that, even though they weren't the ones going into space. They loved it because you were still part of something as it's being built. All right, so enough of my soapbox. Getting into the math of things. So like I said, so logarithms, they're special functions that we can use to display different values in different magnitude and be able to compare them easier than if they were just looking at them linearly. Okay? So logarithms can be expressed in one of two ways. We can express logs in exponential form or logarithmic form. Exponential form is simply as a value to a power gives us some number. The logarithmic form is the log of a base to some value is this. So this is how we can go through and separate these values. So if we wanted to know how many times we have to raise something to get an answer, this is how we would go and solve it. So what we have here is their form. So 10, this is called our base. The x is our exponent. And the 100 is our argument. Same with this over here. We have log of some base times the argument gives us the exponent. And we can go back and forth with these guys. Our calculators are set up to deal with log of base 10. If we want to do a log with another base, we can do it, but we have to take a couple of extra steps because the calculator is not programmed. And really what this is this is looking up on a chart compare to it. So it has, your calculators have charts pre-programmed into it. It just pulls this number up and uses it. So this by itself is just a function returning a value. It's not actually doing anything with the math. So for example, if we had a problem that said we have 6 to the x power is going to give us 2.5. How would we solve for that? First thing we need to do is convert this into a form where we can mess around and adjust with this x. So we want to convert this guy from exponential form with an exponent to a logarithmic form. So what is the base in this equation? 6. So we're going to have log base 6, and then what? Times 225 or 2.5 is equal to x. Now we can manipulate this equation and we can plug this into our calculator. If our calculator had base 6, which it doesn't. So what we have to do is we have to plug this into our calculator. If our calculator allows us to plug in this value, it's not actually going to look up a table based on log 6. It's going to do this next step internally. Some calculators let you do it, a lot of them don't. But the way you can solve this, so we can find this value, is you take the log base 10 of 2.5 divided by the log base 10 of 6. So this way we could find out what number we needed to raise 6 to get it to be 6.5. Yes? Okay. The reason this is going to become important is because we want to be able to solve for this exponent. This is one of the examples I'll get into tomorrow. We'll go through and we'll use this method to solve for it. Basically, what we're going to be looking for is how many years is it going to take us to get to a certain sized hard drive. It's kind of fun. Because like I said, I need to look at it again and make sure I'm current with what we have, our starting point, and prices and things like that to give you guys examples of that. Let's see. So this is any problem that we have involving an exponent. The reason specifically in electronics why we're going to be solving this, or at least the first one we're going to come into, is when we start dealing with capacitors. When we get into capacitors, we have some timing and discharging times that we have to solve for. How long does it take for a capacitor to charge? How long does it take to discharge? Well, what happens if I screw with this parameter? What we have is a formula, and I'll show this to you guys. See if I can remember it right off the top of my head. So our V capacitor is equal to the V final minus V initial times, let's see, V final minus V initial times e to the negative t over tau. Yeah, it's an instantaneous voltage equation is what this is. So what we're going to do is this is the value that our capacitor is going to charge to. Again, with the initial value, or the final value minus the initial value, times e, which we're going to talk about here in a second. E is natural log. To the negative t over tau, where t is time, and tau is the time constant of your capacitor. Tau. And in this case, tau is resistance times capacitance. So where we will use this is we will have to solve for, let's say, all I have is a 1 microfarad capacitor. I need to be able to get a certain tau in to get at my equations. I need it to charge so fast. So what I need to do is solve for this value. Well, we know everything else, but we have it raised to a power. It's inside of an exponent. The only way to get it out is to use logs. Like I said, I know it's a lot right now, and what we're going into, we're talking, this is 2 weeks from now. the material that we're talking about, what we're going to be doing. So, but the idea is, this is why we have to use them, is we have to get this exponent down to where we can manipulate it. Yes?
Wait, is tau a specific, or however you say that, is that a specific measurement like ohms or watts, or is it like a general thing like delta or theta?
It's a specific measurement. It's called the charging constant of a capacitor. It's measured in seconds. How long does it take for this to happen, is the idea. And so we have to get there and split it up to solve for this value. To get this isolated, we're going to end up, we'll put all this guy into a log, natural log. This guy will drop down to the x. Then we can manipulate it just using algebra. Okay?
So it's an exponent like a theta, but it represents something like the other side of theta.
It's kind of a hybrid between those.
I don't like it.
But the idea is we use logs to get at this exponent so we can manipulate it in our equations. That's the whole idea with logs. So getting into this, E, like we said, is the natural log. So your calculators will have two tables essentially stored in them to look up these values. And they're just multiplied by your arguments. So you have log base 10, but you also have E, which is a constant. So E is equal to 2.1424. And what we use, this is used a lot, the little e. Yeah, it gets into engineering, radians, circles, that kind of stuff. But what we do with this is if we have E, we take the natural log, which is the base E of 2.1424 is equal to x. So e to the whatever power. Do what?
I think E has 2.7.
That you're thinking of a different one. A different E. That one's used in engineering specifically. The one we're going to use is going to have this value. But the idea is we can have any E like we have here raised to any power. We have to be able to solve for it. So we have the natural log of these guys. So we solve for them the exact same way as we do with logs. We have our base, which is E. We have our argument, and we have the exponent. We can solve using ln, which is base E, to get us this. We're just going to be touching this very, very briefly this week. We're going to be diving into this more when we get into, like I said, into the capacitors. Different E.
You really throw me for a loop today, bro.
Yes, E is a number. It's a constant. But we're raising it to some power. We have to be able to solve for those powers. Yes, like pi. It's one of the mathematical engineering constants that exist. Your calculators have a function for E. It has a function for pi. It has... Yes, it is kind of weird. But like I said, this is how we're going to manipulate solving for exponents. Tomorrow, like I said, I promise we'll get into some more. This will make more sense when I show you guys this example of what we're doing. So this week, as far as test questions, what we're looking for is just simply converting numbers back and forth and understanding how to convert back and forth between logs and exponents.
So I don't quite understand the log and 2.5 over 1 and 6.
Okay. So our calculators that we have only can do log base 10. They don't have any way to do other logs. It's because it's looking up a value on a chart and then literally pulling that information, using this value and calculating it using something else. So your calculators, when you're using logs, are not actually calculating anything. They're grabbing a constant value and multiplying it by something else. So to save space and to save time in the calculators, we only use log 10 because our number system is base 10. We don't care about any other number systems right now, but there may be times where it happens, like this one. So if we wanted to know what power do we need to raise 6 to get to answer 2.5? we would be able to take this, convert it into the logs, and then when we put it into our calculator, because it doesn't have the log space 6, we plug in log of the 2.5 divided by the log of 6. I'm not exactly sure why we do that. Just that's what we're supposed to do to be able to convert these logs into different bases. Because there's only so much memory in calculators. You know, even standard scientific calculators can do logs. And all it is just pulling information off of a chart. Yes, Dylan, do you have a question? Okay. So, for example, in the quiz, we are going to have this. And why am I changing language? Yeah. Okay. So if we have 10 to what power will give us 1700. So think for in examples in this equation. Whatever, let's just say all this information in here comes out to be 10. We were trying to get a total value of 1700. What do we have to raise our 10 to get that value? This is where we're going to use logs. So we take, this is our base, this is our argument, and this is our exponent. Okay? We convert this into exponential form to convert it into logarithmic form, so that way we can solve this value. This could be a fraction, and we want to be able to get there. So we take our log of our base, in this case is 10, times our argument, which is 1700, equals the exponent. So now we can take this and we can plug this into our calculator. Log base 10 of 1700. So if you do that on your calculators, you take log, and on mine it just gives me a log and then it gives me a parenthesis for the argument. So I put in 1700. It gives me an answer of x equals that. So basically what we're saying here is if we take 10 and we raise it to this value, we're going to get 1700. So 3.23 times of taking 10 gives us the 1700. This is going to come in handy, like I said, when we're using our instantaneous voltage equation, when we're trying to solve for how much time is it going to take for something to occur. How much resistance do I have to have in this circuit to be able to solve for that? All we're, go ahead.
Since the base is 10 already, we don't have to do that division.
Correct, because it's already in base 10. And that's what your calculator will do.
But if it was not, so if it was like a 9 raised to exponent, then it'd be the log argument over the log base.
Correct.
Okay.
So that's just the conversion we can do. If your calculator allows you to put in a different log besides 10 for the base, that's what it's doing. It's going to automatically divide those out for you. You just don't see it. Okay? So the same thing, if we put 9 to the x is equal to 1700, how many times do we have to raise, or what power do we have to raise 9 to get this value? We would solve it the same way. We would take log of base 9 times the argument of 1700 gives us x. Calculators cannot do base 9, so it becomes log base 10 of 1700 divided by log base 10 of 9. So all it is, and all we're doing is just a conversion from getting this exponent by itself to solve for it. And we can go back and forth as well. We can solve for, if we have log of 10, so log base 10 of some number is equal to 3. Basically, what is this saying? Ten to the third equals some value. So we can go back and forth with these guys. And that's the whole idea of what we're doing with logs this week, is just this conversion going back and forth and solving for a value. Application of logs is going to come when we start talking about capacitors. Come on. So same with this. If we wanted to go with e to the x is equal to 1700, how would we solve that value? Yep, so basically we're going to take the natural log of both sides. Those two are going to cancel. So we're going to have x is equal to the natural log base e of 1700. And we can solve for that. So all we're doing is we're canceling and moving logs to get this exponent to drop. Just like we did with these guys. If we put the log of this guy, the 10 is going to fall away, and we're left with the log base 10 over here. Think of them as opposites, the inverses of them. Just like when we have resistance, when we take the inverse of resistance, it gives us conductance. Same thing with this. When we take the opposite or our inverse of the natural log, we get E. When we take the inverse of logs, we get 10 to the x. Don't overthink these guys for this first week. Like I said, all we're doing is just primarily going from back and forth between logarithmic form and exponential form. How can we solve the value? What value do we need to get these to be equal? And the because is when we get into capacitors. Thoroughly confused, you guys yet? It's like I said, it's kind of hard, but the idea is we can calculate very complex systems now, because now we have a way to manipulate that exponent. We didn't know how many times without plugging and chugging or trying to get certain values with an exponent. But now we can be able to isolate that exponent and then manipulate it as we need to. Which again, like I said, the instantaneous voltage equation is our primary use of transferring exponents down to be able to manipulate them. We okay there for now? Okay. Now, like I said, so this one, there's a lot of complex stuff going on just because this is getting ready for AC. We're in the last couple of weeks of DC. We're getting into understanding how AC works and solving for things like that. This next little bit, we won't touch again until we get into the AC portion. But I want you guys to at least be exposed to this beforehand, so that way when we start jumping into there, you're already been exposed to these ideas and thoughts before we start solving. The next part we have is complex numbers, or imaginary numbers. How many people have heard of imaginary numbers and logs before? How many have used them? Yeah, roughly, vaguely. Okay, so the idea behind imaginary numbers is in the world of electronics, we don't always deal with just positive numbers. Okay, we're going to come up to situations where we have negative values, where we have negatives inside of square roots. We have to be able to account for those and solve for those so we can plug them into a calculator. Because if you put in the square root of -1 on your calculator, what does it do? Domain error, non-real result. The calculators are not programmed to handle values. Your calculator is looking at things like this. It's looking at them on a number line, left to right. But now what we're doing is we're looking at numbers left and right. Now we're adding up and down to it. So when we start talking about this, now we're telling our calculator to start looking at one-dimensional numbers, to start looking at two-dimensional numbers. And by themselves, they can't do it. Do what? Yeah, we can't see it. We are 3D creatures. We can't see into the fourth dimension. Not to say that there's not things that can see into the fourth dimension, but, and even then, we have trouble looking at the two dimension, the second dimension, looking into depth. Okay? How many of you guys have seen the movie Inside Out? Few people? They kind of do an idea of what they all look like. 3D is you can move in 3 dimensions. 2D is all you're really looking at is either a flat surface, or if you look, you're looking on forever. Okay, in one direction. But you have a wall in front of you that you can't see past. All you can see is to the left or to the right. And then you become a point, which has no depth, no nothing. It just is there. It just exists. Yeah, even some of that's actually a good thing. Going from Mario, like in the original NES, was 2D. Could only go side to side. Now you get into Mario nowadays, now he can move and go wherever the heck he needs to go. It's more built real world. I don't disagree. So, we have to have a way to be able to solve for these guys. Now, imaginary numbers are what we use in the math world, the science world, engineering world, to be able to explain and understand how things are working and how things are moving. One of the primary reasons, like I said, is to be able to solve for a negative inside of a square root. Calculators cannot handle doing a negative inside a square root unless you have special functions turned on. Basically, those tell the calculator to ignore what it thinks is the rules. These numbers are not tangible. And by tangible, I mean things like 10, 15, pi, e. Those are actual numbers that exist. The idea behind imaginary numbers, and one of the reasons we're going to learn to it in AC, is when we're dealing with capacitors and inductors, they are going to have a resistance of sort. It's going to be called reactance. A capacitor will oppose AC current using the reactance. Okay, the more conductance, more inductance you have, it's going to change how much quote unquote resistance there is to the circuit. It acts just like resistance, but there is no way to physically measure that amount. You can see the effect, we know it's there, but there's nothing we can do to measure it. It only exists in theory and in calculations, but we can see the effects of it afterwards. So this is kind of getting into, string theory, dark matter, that kind of stuff. It's there. Black holes, same thing. Black holes, sometimes you can't see them. They're very, very small, but they have an effect on the space around them. And there's no real way to get solid data out of a black hole. We know they exist, but they're still one of the things we don't know a whole lot about. So what we have is to define these guys. If we have the square root of -1, Depending on if you're in math or in engineering, they're going to use this in two different names, but they mean the exact same thing. It either equals I or J. Yep. Okay. The square root of -1 is referred to as I or J. Depends on where you go to school. Even in between electronics, people swap them out between I and J. So in this class, we're going to use them interchangeably. For all intents and purposes, they're interchangeable. I don't care what you use. That what? Yeah, I started looking it up one time, and I got about 2 words in, and I said, to hell with this. It was way over my head as far as what they were arguing about, and so I'm like, I'm going to use them interchangeably. Yeah. That's probably how it started, is somebody had it slurred when they said imaginary. So with this base definition, if we have I squared, that's going to be equal to what? -1. Because if you have the square root of -1 squared, that square root is to the 1/2 power times 2, gives you 2 over 2, which reduces it down to -1. So some of the things we're going to be doing is, as we go through these problems, we're going to be multiplying functions together. We're going to have, so for example, we would have a resistance value that would look like this. And I kid you not, this is a real value. This would be for an inductor. We would have 85 ohms of winding resistance plus the reactor, or the reactance part, the coil of wire, is going to be adding 30 ohms of reactance to the equation. We have to take those into account. Yes. Real. It's the winding resistance. So basically, it's a big coil of wire. You can put your meter on it, and you'll measure 85 ohms from just having the wire that's there. But we also have the reactionary part of this inductor. And the inductor reacts to frequencies. Depending on the frequency, that value is going to change. So the idea behind this is we're going to have values like this. We're going to be multiplying them times different values. So if we had like 2 inductors in parallel, we would go through this. So now what we're going to talk about is understanding some of these bases, because we're going to get them when we can simplify them down. So this would be 85 squared plus j of 60 plus j squared times 30, or times 90. 900, whatever it is. Okay? So now we have this problem, but we have a j, which we know is the square root of -1. All it's doing is designated as an imaginary value. It doesn't exist. It's on a different phase, different plane of existence, really. But we have j squared, which is -1. So this becomes -900. So now these two values are going to add up, and we come back down to a single value with an imaginary portion to it. So with this, we want to understand the powers of j and how they work. They will follow a pattern, so we can determine how we can simplify this down and make our lives easier. So if we have I to the power 0, what is that value? 1. And why? Anything to the 0 power is 1. If we have I to the first, that equals I, just equals itself. If we have I squared, what does that equal? -1. And if we have I cubed, -I. because I squared is -1, I to the first is I, you combine them together, you get -I. Okay? What if we go up again? I to the fourth. Let's find it out. 1, -1, I did hear -1. Just 1. Okay, why? I squared times I squared is I to the fourth, right? What is I squared? -1. -1 times -1 is 1. I to the fifth, it's I. Because we already know what I to the fourth is, it's 1. We're adding another I in there. 1 times I is I. I to the sixth, -1. Yeah, so now it's in a pattern. All we're doing is we're just looking at these powers of I, because there's going to be times where we're doing these multiplication problems, things like that. We're going to end up with, in this instance, like we had I squared, I or j squared. We need to quickly solve what would that be. If we learn this pattern, I squared is -1. Because then when we simplify it, now we're left with just an imaginary number and a constant number, a real value. The other way to think of this is because when we multiply these guys together, we have some value. We're trying to create the new point between the two of them. Okay? So what we end up with is we have our real value, and we have is what our graph is going to look like. We don't have a j because we're not going into the next dimension yet. We don't have a z-axis to account for the squares. Huh? Yeah, thankfully we're not going into the z-axis yet. Yet. You'll get there when we get into calculus. So, but the idea here is we want to reduce these values down to just a single coordinate of a real value and an imaginary value. So anytime we have powers higher than 1 or 2 of j, we need to be able to reduce it down to a simple value. That's the whole idea behind this. So when we see these, we have this pattern that's going to be wrapping through like this. So I to the seventh, -I. Because it's all building up on the previous one. And this pattern is going to repeat and repeat and repeat. The pattern is going to continue up. So if we had I to the negative first, what do you guys would suspect we would have? We'd have -I. This pattern repeats even when we take this exponent and get smaller and smaller and smaller. So if we had to the negative first, would be -I. I to the negative second, I to the negative third, I to the negative fourth. That pattern's still going to continue and repeat. So the idea is, now we can, now that we have this pattern that we've established, now we need to figure out, in case we come up with something that, these are going to be a little extreme, but the idea is if we have values that we multiply together and we end up with, let's say, a j to the 200. Whatever we were doing, we were multiplying values together and we ended up with a j to the 200. How would we figure out what that value is without having to write out the whole list till we get to 200? The rules are, we need to convert to a known power so that way we can simplify it. So if we look at this, let's see, 4 times 50. So if we split this up, we know that 200 is 4 times 50, right? What is the power? And we know that this is going to turn into j to the 4th raised to the power of 50. Now we're splitting up the rules that we learned at the beginning of the semester with powers of 10. So when we have a power raised to a power, we multiply them together. To divide them out, we're going to split them back into their raised to a power. So what do we end up with here? What is j to the 4th? 1 raised to the 50th power is 1. So j to the 200th is 1. Okay? So really, all you have to memorize is these first 3. Because then everything is just going to be multiples of that. Okay? So if we have j to the 501st power, how can we split that up to make it easy to solve? How can we split that up to make it simple? Okay? What's j to the 1st? Or I to the 1st? I. So this goes away and we just have our j or an I. I switch back and forth between what I'm using. I usually try to use j more often, but there's times that I go back and forth between them. Like I said, just know that they're interchangeable. So this 500, how can we simplify this value? Huh? 3 and 100, we could do 300 and 200, because we got to get back to 500. What about using this previous one? How many groups of 4 are there in 500? 125? So we could expand this to be j to the 4th times 125. And that turns into, what is j to the 4th? 1 to the 125th power. And this is actually not plus, it's times. It's not easy on the eyes, I get that. That's why I'm talking more than showing, because this stuff's kind of hard to show on a thing. Trying to condense these into notes that I could actually read later was difficult. Okay, I will post these online as well, so that way you guys have access to them to go back through and look over what I said, what we've been talking about. It does lay it out a little bit more linear than what I have it written up here. Yeah. Okay. Like I said, the key is to memorize the pattern. J of 0, J of 1, J of 2, J of 3. Everything else is going to be based on these values. Okay, and then you'll split them up and basically solve them independently. So like here, we split it up. The J of 500 times J of 1 gives us that 501. We know what this value is, and if we can get this into a multiple of 4, that'll make our life a lot easier, because J of 4 reduces down to 1. And then 1 to any power is 1. So that's kind of one of the clues and the key things that we can do. Separate out a value from 1 to 3, j to the 1st, 2nd, or 3rd power. Your other value, you want it to be able to split up into a multiple of 4. And then with that, you can solve pretty much any value that comes at you. Okay. take the quizzes. Like I said, I know there's a lot of information I just shoved down your guys' throats. A lot of information. Okay? Go home, at least look over the quiz for the logs. There's common logs and natural logs. All they are is the difference between using log and ln. That's the only difference with those. We have the quizzes for imaginary numbers that we've just started talking about, which are the i's. And so then we will start talking about complex numbers here in the next day. So take those quizzes. If you fail them, you fail them. Like I said, you get the highest grade. It doesn't matter how many times you take the test. Come back with questions tomorrow and we'll kind of pick up from here.